Dr. Kong. Hello, Dr. Kong, Assistant Professor at University of Utah. It's a delight, it's a pleasure to have you on the stage. And this is also a really interesting piece of work, in my opinion. Very interesting research, very interesting publications. And this one is about digitally embroidered liquid metal fibers for e-textiles.
Okay, thank you. Thank you so much again for the kind invitations and for having me here. I'm very fascinated by exciting works of previous speakers and looking forward for potential collaborations. I'm currently an assistant professor in the University of Utah in the mechanical engineering department, and I primarily work on the 3D printing of electronics. Today, I would like to highlight the new research directions we have been very excited with in collaborations with Dr. Rongzhou Lin and Professor John Ho from the National University of Singapore, specifically on the digitally embroidered liquid metal electronic textile. The integrations of bioelectronics with the human body could have a significant impact in the field of diagnostic, drug delivery, and smart prosthetics. Yet, as you know, such integration is inherently challenging due to the geometrical, mechanical, and material dichotomies between conventionally manufactured electronics and our human body. For example, in-body implantations of bioimplantable electronics, they are very powerful but require a surgical process that in the short term causes pain and discomfort, but in the long term carries an inherent risk of infections and eliciting inflammatory immune responses, as you can see in this human trial that involved a drug delivery electronic device. My research strives to overcome these dichotomies. My previous and current work focuses on developing a multi-scale electronic 3D printing approach that can create electronics that can better interface with a three-dimensional construct. Further, recently we also developed ingestible gastric resident electronics, which is an electronics that can be swallowed and stay in the stomach for weeks, allowing the integrations of electronics into our body without requiring a surgical process. Now, recently we started to have significant interest in textile electronics as we envision a synergy of such technologies with 3D printed wearable and ingestible system that we have been developing. In comparison to wearable and implantable electronics, right, electronic textile are very attractive here as it leverage our inherent needs in clothing, which obviates the intrusiveness and risks often associated with, say, implantable and even wearable electronics. There's been tremendous amount of exciting work by many of you that demonstrated what electronic textile can do. For example, here's a work by Xu et al., which really shows the power of, for example, creating display in textile that can express the thought of the wearer, which is really a powerful tool. For example, if I can see my audience listening to my talk and see what they are thinking, I can adaptively change my talk depending on whether you're hungry or are bored with what I'm talking about. Indeed, there's a lot of potential of what we can do with e-textile, from sensing, display, to even actuations. But one of the key criteria for this to be successful is that we have to achieve all these complex functionalities without causing discomfort or interference with our day-to-day activity. Now, this has been challenging due to the inherent rigid and planar natures of conventionally manufactured electronics, as we talked about earlier. Importantly, textile is a porous structure composed of flexible material that has been designed to endure repeated mechanical, thermal, and chemical stress from sweat and daily activities. Now, if you're not convinced that we are causing tremendous stress to our beloved textile in every day, this is one of the few example where it's my t-shirts where every once in a while in my graduate school, right, they will give out free t-shirt that is actually comfortable. But as you can see, over time, they start to disintegrate even in a few years. So indeed, we are adding a lot of stress to our textile. And what are the existing solutions for textile electronics? Right? How do we introduce these functionalities in a durable fashions without interfering with the day-to-day activities? There are two strategies. One is we can first miniaturize and package those electronics into a very small form factor, such as in this case, creating what we call button size electronics. And that's pretty cool because now we can pretty much use it as a button that we need anyway for the clothing and attach that to our regular clothing as either part of functions or for decorations. But obviously that also constrain our device to just a button size footprint, right? Anything bigger, it starts to feel a bit awkward and it starts to interfere with our day-to-day activity.